Question 16. This question is about ions and compound having hydrogen. A. Lithium aluminum hydride LiAlH4 contain the aluminum hydride ion. Draw a dot and cross diagram to show the bonding in aluminum hydride ion. Show outer electron only. Okay, so the clue is on the hydride. There are three types of hydrogen here. So if you have normal hydrogen, so you just call that hydrogen. If you have hydrogen plus, we call that proton. That means it has lost an electron. So that would be like H losing an electron to become H plus E minus. So that's hydrogen proton, and that's hydrogen, so that's a proton. There's another one that says hydrogen hydride. So that's hydride. Hydride is when you gain an electron, so that's H plus E minus, we give you H minus. That's an hydride. So that's hydride, proton, and hydrogen. So the clue is given to you here. Hydrogen hydride is hydrogen with 2 electrons. Hence it's minus. This is hydrogen with 1 electron. That's just hydrogen. This one is proton, is hydrogen with no electron. So just stick a plus there. So, but with 2 electrons, we stick a minus. So that means if we say aluminum hydride, we mean something like this is coming into aluminium. Now, aluminium is in group 3. You might say group 3 if you're in UK, that one. So that's aluminium. Or group 13 from US. So that's USA and that's UK. So that's USA here, group 1, group 2, group 3. This is all USA. Or that's group 18. We call that group 0 or group 8. So that's UK. So this is UK here. The above one is UK. Right. So that's aluminium. It's got 13 electron and 13 proton, which means that it's got 3 electrons in the outer shell. That's why it's in group 3. So aluminium having 3 electrons in the outer shell, 1, 2, 3. In fact, if I write the electron configuration for aluminium, so aluminium is going to be would be 1s2, 2s2, 2p6, 3s2, 3p1, which means this is the outer shell. So we're using the outer shell, the 3 electrons, 1, 2, 1, that's 3. Right, so if you draw the outer shell, that's 3s orbital, that's 3, let's just put it 3s orbital, and then you're going to get 3p, that's 3px, that's 3py, and that is 3pz. So you can see there are 2 electrons here, so that's 1 electron, 2 electron. Maximum electron in an orbital is 2, and that's 1 there. Okay, and these 2 are vacant. Because they're vacant, this electron here is promoted from 3s to that. So the excited state of aluminium is going to be this. This is the excited state of aluminium. So that will be 3s with 1 electron there. And you can see now that there's a 3px with 1 electron, and that electron has been promoted to there, so that's why you get 1 electron there. That'll be 3p, that's 3p y, and then you got the vacant p orbital here, so that 3px, the 3pz. So this is a vacant orbital. So that's what's going to happen here. This orbital here is vacant to form the octet. So hydrogen can come in to form a bond here. So you can see now, that's what we're going to do now. So we're going to get hydrogen here. That's hydrogen with 1 electron. That's hydrogen. So this is aluminium. That's hydrogen, 1 electron. And they form a bond. So here is the bond they form. So that's what we're doing there. So I'm putting hydrogen here. Okay. And the second hydrogen here, there's 4 hydrogen. So the second hydrogen comes in to form another bond. So that's hydrogen with 1 electron. And so you can see that that's another hydrogen there. And the third hydrogen comes in to form a bond. So that's third hydrogen there. So that also form a bond. So I can write that here. This is hydrogen. And that forms a bond. So those are 3 bonds here. Those are the 3 bonds. Now what's happening with the fourth one? The fourth hydrogen is an hydride with a negative ion. So the fourth hydrogen comes in, and this one has got 2 electrons already, and then doing dative covalent bonding. So that's dative covalent bonding, all goes into there to share. So now it thinks it's got 2 electrons, 1 from hydrogen, 1 from there, so they're sharing that basically. This is electron now going in there to share. Okay, so now here is the dative covalent bonding. Here you go. And this hydrogen has a negative value here because it's got the 1 extra hydride, it's got an extra electron. That's why it's minus. This negative is now being transferred to aluminium. So now the structure of that aluminium can be drawn properly by just doing the AL. Remember, that's aluminum bond there, and with the dative covalent bond, this is covalent bond, that's covalent bond, that's covalent bond, and this one is dative covalent bond. And then the structure can then be drawn like that, and it's taking minus there. So that's the structure we're looking for. And so this is the knot and cross diagram that we want to do. So I can do the cross diagram here to just make it look easier. That's cross, cross, or dot and cross, and that's cross. So aluminum is a cross. And to put a negative sign, I can stick the negative sign here and stick a minus there. So that's what that is. So you can draw it that way, you can draw it this way. But this is a dot and cross. That's a dot, that's a cross. So it's got 2 crosses here. So that's why it's negative. And the negative is transferred there. So let's take that away. And that's the negative there. Okay, so that's the structure for that one. And this structure is what we call tetrahedral because it looks like carbon. Tetrahedral. So we can call that tetrahedral. Okay, and the bond angle for that is this is shape, and the bond angle will be 109.5 degrees. Likewise, the second one here, the B part, so that's how that forms. The B part is also forming in a similar fashion. So let's do that one. we've got nitrogen. So that's aluminum here. Ammonium is similar to aluminum because it's got 4 bonds here. That one is tetrahedral 109.5, and this one is non-linear. So you can say non-linear, or you can call it bent or V shape. And the bond angle is 104.5. That's similar to water. So that's linear, non-linear. Okay, so how do we get that one? It says predict the shape. I'm already telling you that's tetrahedral. So how do we predict that shape? Well, for the nitrogen is in group. You quickly look at that. So nitrogen is in group 5 here, or 15 if you're in USA. Group 5, and it's got 5 electrons in the outer shell. And so if you do nitrogen, you would have well, nitrogen is 1s2, 2s2, 2p. Nitrogen is group 5, so, and it's got 5. It's got 7 electrons altogether. So 2p3, and that's the nitrogen there, which you can write. The outer shell is that one. So then you can say the outer shell. So I'm just drawing that, and the p orbitals are like that. So this is nitrogen having the outer shell has got 2 electrons, 1 there, 1 there, 1 there. Okay, so how do we form NH4? So we are coming from the H plus, and there are 2 clues to these ones. We're coming from the proton. We're coming from that. That means no electron there. And here we're coming from hydride with electron. So you can see the 2 differences here is using those 2. So for this one, we're using that one. So we got hydrogen that doesn't have an electron. So with a hydrogen that doesn't have an electron, we can stick that here. You see, that's hydrogen with no electron, vacant orbital of s orbital for hydrogen. So that's hydrogen, no electron. So that would be gaining 2 electrons from dative covalent bonding coming to there to share the electron. So that's a positive on hydrogen there, and that positive is transferred to nitrogen. And the other hydrogens, they have 1 electron, so that's hydrogen with electron. This is normal hydrogen, and they will form, so that's H here. So that's dative covalent bond, and that's normal bond. Okay, so that's normal bond, normal bond, normal bond. So that's covalent bond, covalent bond, covalent bond, dative covalent bond, where this is supplying both the bonding electron to hydrogen. So that plus is then transferred to nitrogen, and that's why you go NH4. Yeah, and that shape is tetrahedral because you don't have any lone pairs. No lone pairs, right? Because there's no lone pair, it's tetrahedral. All bonding pairs. So there's 4 bonding pairs, and that's why it's 109.5 degrees. This one here, the nitrogen from the NH2 minus, it's pretty similar to that, except if you go to nitrogen here. So we got nitrogen, and we got the outer shell. So this is outer shell, by the way. So remember, that's P, that's 2S, that's 2px, 2py, 2p, Z. 2s, 2px, 2py, 2pz. You see that it's got 2 electrons there. 1, 1, 1. But the hydride coming in has got its own electron. So there's an hydride coming in there. So it's got 2 electrons. Right? There's hydrogen there. So there's hydrogen. And this is a lone pair. It's not having any effect. This 2 electron pushes that electron away to another one there. Somehow you get these 2 electrons being donated to there, where that electron is promoted to there. Okay, so now you now have got 2 electrons here because it's promotion from there, so that disappeared. So you got 2 electrons that goes in there, and then you've got your normal hydrogen bonding going on here. So that's just a normal hydrogen bond forming a covalent bond there. So that's a covalent bond, and that's dative covalent bond. And because this one comes with a minus, obviously, remember that came with a plus, the plus transferred to there. This one comes with a minus because H minus, right? So that minus is transferred to there. So you've got 2 lone pairs, just like you got 2 lone pairs for that one, just like water. So the structure for that will be, if you to do that structure, you're going to get that one, NH4 is tetrahedral, so that's NH4 with a plus on there, hydrogen, 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 which can then be drawn by just doing N, H, 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 H with a plus. Right, but this one here, that one will now be drawn as N H H with the 2 lone pairs sitting there. These are the 2 lone pairs, and that's hydrogen and hydrogen. But this one came with an electron, right? So that electron is there. So if we draw that one, that will be the electron there. So that's because you can see it, lone pair, because that electron here is being promoted to there, because this energy is far too greater, pushes that to there, hence donates that to there, and forming this. And so that's the shape you get for the NH2 minus, and this is NH4 plus. And that's the structure for and that's why this is similar to water, very similar to water, which is H2O. Water looks like that with the 2 lone pairs, and that's H, H, and that bond angle here is 1. That bond angle is 104. Excuse me, 104.5 degrees. So because it's similar to that, because you've got 2 lone pairs, 1, 2, and the bonding pairs. So bonding pairs, 2 lone pairs, similar to water. Bonding pairs, 2 lone pairs, hence it's going to be 104.5. Tetrahedral, similar to CH4. No lone pairs. So if you're looking at the CH4 here, yeah, so there's a CH4 there. No lone pairs, 0 lone pairs, so 0 lone pairs, okay, and that is 109.5. No lone pairs, 0 lone pairs, 109.5. Now the C part here is not too bad because we're looking at the nitrogen compound, phosphorus and arsenic. They are all in group 15 or group 5. So again, looking at the periodic table, you can see group 5 or group 15 is nitrogen, phosphorus, and arsenic. The electronegativity of that and that, this is obviously 4. Electronegativity is 4, 3.5, and 3. So that will play a part in the next discussion as electronegativity values. The boiling point of the hydrides are shown below. The boiling point is that, so when I draw, this is 0, and if you go down the negative side here, you can see that one will be a minus 88, and that will be pH3, that will be minus 55, that will be ASH3, and that will be minus 33, that will be NH3. So why is the boiling point like that? Explain why the boiling point of pH3 is lower than the boiling point of NH3. And if you look in the periodic table, I mean, you expect the boiling point either to increase down the group because they're getting bigger and bigger. So you expect that boiling point here to be bigger than that. But ammonia seems to have the highest boiling point than phosphorus, but arsenic has got highest boiling point than phosphorus as well. So what's going on? So what is going on is that in the structure you can form hydrogen bonding because of difference in electronegativity. The electronegativity between nitrogen and hydrogen will cause it to form hydrogen bonding. Electronegativity between oxygen and hydrogen will make it form hydrogen bonding. Between fluorine and hydrogen will make it form hydrogen bonding. So the key part for the NH3 is the hydrogen bonding. So NH3 will have or will form hydrogen bonding. Now, what is hydrogen bonding? Well, hydrogen bonding is if I draw the structure of ammonia and so the structure of ammonia, because let's say this is ammonia, so that's N with a lone pair, hydrogen, hydrogen, hydrogen. Because there's difference in electronegativity, this will be delta minus and that will be delta plus. Another ammonia will be here with another H, H, H with another lone pair, that's delta minus and that's delta plus. Now, between these two, because that's delta plus, they will form a hydrogen bonding there. So there's the red one is the hydrogen bonding. If I put another ammonia here, it will be N with a lone pair and H, H, H. Then that will form hydrogen bonding between these two pairs. These two will form hydrogen bonding and that will form hydrogen bonding. That bond here and that bond, they call hydrogen bonding. So that's what hydrogen bonding is. Why? Because there's a difference in electronegativity between the nitrogen and hydrogen. Nitrogen electronegativity is, we said, 3, and hydrogen is 2.1. This one is 3.5, and that's 2.1. And this is 4, and that's 2.1. But we're looking at this one. Okay. But pH3 will not form hydrogen bonding because the electronegativity difference, the pH bond difference is roughly, in electronegativity is roughly 0. So the electronegativity between the two of them is very, very small. So hence it could not form hydrogen bonding. Right. And if it has hydrogen bonding, that's an extra bond that you have to break. So this one has extra bond you have to break, hence it increases the temperature. So therefore you have more energy, all right? More energy is required to break the intermolecular bond. Intermolecular bond inside. So that we're talking about breaking this bond between ammonia and another ammonia. You have to break that bond. Apart from all the other bonds they all have the dipole bond, but the extra bond that ammonia here has is hydrogen bond, and phosphorus pH3 does not have hydrogen bonding, and that's what makes it stronger. And what about, and that's why it increases the boiling point of ammonia, hence boiling point is higher in NH3. Now, explain why the boiling point of pH3 is lower than the boiling point of arsenic. Well, arsenic has more electrons because it's bigger. So arsenic H3 has more electrons than pH3, and so arsenic has a stronger induced dipole interaction. So that's why. What do we mean by that? So a dipole interaction is that if they're neutral, but the electron here will push the electron here away, making this one positive and this is negative. So what do we mean by that is that to say, okay, if this is one substance and it has electron here, this is negative. This electron will repel any electron here, push them away, making this side positive for another molecule. That's what we call induced dipole. You're creating a dipole by one side of electron pushing the other electron to the other side, making this side positive. Because you made that side positive, we call that induced. And that's what the induced dipole is.